Welcome back. In the previous video, we studied the graphs of sine and cosine functions, the most important and also the most confusing because they're so similar and differ by sign. Sign I mean by plus and minuses. The others are not as confusing. Look at the tangent function, and here is the graph of the tangent function. It's not that bad. We have vertical asymptotes, but that's because tangent is sine over cosine, and whenever denominator hits 0, we expect vertical asymptote. Here in this picture, in the standard domain, negative pi over 2 to pi over 2, we have this thick blue curve, and the others are just periodic behavior, the same thing coming over and over again. The period here is pi, not 2 pi. And here is the visualization of the tangent function using the similar type of animation that I use for sine and cosine. It's not as effective as sine and cosine case, but here it is. Let's try to decipher what is going on. In the left-hand side, you have this unit circle, and blue arc represents the angle, the size of the angle, the counterclockwise direction of the arc length on the unit circle. So that's the angle going from negative pi over 2 to pi over 2. Actually, negative pi to positive pi, excuse me. And whenever that the terminal point hits the y-axis, consequently x, the horizontal becomes 0, the denominator is becoming 0, and thus we have vertical asymptotes there. So vertical asymptote at negative pi over 2 and positive pi over 2. And of course, this is periodic, so same thing continues. And is there something from 0 to 2 pi, or is it really necessary? I don't know, let's see this for fun. We have this triangle showing up, and then again, whenever the terminal point hits the y-axis, we have vertical asymptote. Okay, same behavior as before, except that this time we are starting from the angle theta equal to 0. But the previous animation was a little bit more interesting. This one is more interesting even, and important too. Tangent, let me remind you again, is sine over cosine. And whenever the denominator, the cosine, hits 0, we have 0 in denominator, so we have vertical asymptote. Not coincidentally here, whenever the green curve hits the x-axis, we have the vertical asymptote. The red is a sine function. Here are some further properties of tangent function, not as confusing as before. Period is pi, so adding or subtracting pi will not change anything. So sine of theta plus or minus pi is just tangent of theta. And tangent function is an odd function. We saw the graph. So tangent of negative theta is negative tangent of theta. Okay, that was easy. And the others, tangent of 0 is 0, tangent of pi over 2 is undefined, tangent of pi is again 0, and this is just one period, so the same thing repeats over and over again. Not too difficult. What if we add or subtract pi over 2? This time tangent and cotangent intertwine. The reason is because tangent is sine over cosine, isn't it? And then if you add pi over 2 to sine function, it becomes cosine. And if you add or subtract pi over 2 to cosine function, we have a sine. But then again, we have plus or minus issue, the sine, SIGN sine issue. And that's what makes this thing a little bit confusing. You have to be careful about those pluses and minuses, but the pattern is the same. Adding or subtracting pi over 2 or subtracting from pi over 2, tangent and cotangent will flip-flop. About which sign, about which plus or minus, you can either deduce each one of them from the scratch, which is rather time consuming, or you can look up. It's if you look at each individual formula, it's easy and easy to deduce. It's just that so confusing because of all those pluses and minuses. Now, let's go over to the other reciprocals, cosecant, secant, and cotangent. Let's go over to cosecant. And the red graph is sine function, and sine function bounces back and forth between positive 1 and negative 1. And if you take the reciprocal, the maximum is, well, we have touching at 1 or negative 1 like those. And whenever sine function hits 0 or the x-axis in this graph, we have to have vertical asymptote. Pretty natural. Same behavior, exactly the same behavior, only shifted a little bit toward the left. It is secant and cosine function. The same behavior. We have vertical asymptote whenever cosine function hits 0. And cotangent function, 1 over tangent, and also cosine over sine. So you can identify where we have vertical asymptotes. In the last picture, cotangents have vertical asymptote whenever sine function, the red graph, hits 0. The graph of cotangent function is very similar to the graph of tangent function, as a matter of fact. It is just flipped, vertically flipped, and then shifted version. And that's because of the relationship between sine and cosine. You can easily deduce that. But that's so 19th century type. Here in 21st century, you have the grapher. So here are the graphs of cotangent function. That's about it for graphs of sine, cosine, tangent, and then other trigonometric functions. Now, where do we use all these? Well, let's do a little bit of applications of section 3 first, and then come back to section 2 and do inverse trigonometric functions, and then let's go back to section 3 a little bit. So what we do in section 3 of this notebook here is kind of open-ended. Here are some applications of some composite trigonometric functions. And x plus sine of x squared, and we have this kind of graph. And here, well, we have computer grapher here, so we have something like this. But if you use your own brain, what is pretty clear is we have a fluctuation around y equals x, because this is a red line, and sine of x squared, this may behave weirdly, but the one thing that is certain is the fluctuation is between -1 and +1. So the function value will not be too terribly different from f of x equals to x. So this is basically an axis of oscillation, and then oscillation between -1 and +1. And that behavior will be much more prevalent if I go over to longer domain, negative pi over 2. Okay, what if I go from -5 pi to +5 pi? We have, well, this kind of fluctuation, and we have axis of oscillation, which is a line, and then we have really wild fluctuation between -1 and +1 if I go sufficiently far away. So moral of the story, if you have sinusoid, especially sine and cosine, then we have oscillation between -1 and +1. We'll have something similar here. Axis of rotation this time will be a parabola, y equals 1/2 t squared. and then the sine of t to the fourth power over 3 will give us the fluctuation. And this is a graph. We have a parabola, the axis of oscillation, and then we have oscillation between -1 and +1. If I go a little bit further, -2 pi to 2 pi, you'll see, well, this kind of fluctuation. Let's go back to -pi to +pi. Aesthetically, it is a little bit more pleasing. So that's one aspect of composite trigonometric function, axis of oscillation. Another important aspect is envelope. We have some function times a sinusoid, sine of something or cosine of something. We have fluctuation, we have oscillation between -1 and +1, but times that. So plus of this one and minus of that highlighted part will become bound of these functions, and here they are. The sine of x cubed part, this part, will be fluctuating between +1 and -1. So +1 times this is the top curve, top parabola, and then -1 times this highlighted will be the lower parabola, and we have bouncing between those two. And those two red curves, those two parabolae, are called envelope. If I go from -2 pi to +2 pi, I think I can see things a little bit better. Yes, we have the envelope here, and we have fluctuation between these two. And here is another example of an envelope. Oh, excuse me, we have both, as a matter of fact. We have axis of oscillation here, and then an envelope. Let's see. Oops. Okay, did I have one? Okay, all right. And then 1 of x squared, that's going to be parabola. And then cosine of x, this cosine part will become as big as +1. So this one times that. So the function down below, 1/2 of x squared minus of that will be one envelope. And when this cosine part is negative, negative plus, so this one will be the other envelope, and we are going to have fluctuation between those two. -pi to pi. What if I go from -2 pi to +2 pi? Well, we have clear enveloping behavior as we expected. This example is called damped harmonic oscillation, and this is very, very important in physics. For example, if you study oscillating spring in some medium like water and even air, we have resistance, so slowly the fluctuation goes down to 0, and we have this kind of envelope behavior. Even better example will be electromagnetism, and of course electricity eventually loses energy and everything dies down, and through resistance or through electromagnetic wave we lose some energy, and this is very typical for alternating currents. And one more, this kind of behavior is beads, and that appears when imperfectly tuned oscillators are interfering each other. And for example, if you get on a propeller airplane, you see things like these. This omega-1 and omega-2 are supposed to be very similar, and if you just get the envelope and you get a third graph like this, and you have kind of sound coming from those beads.